Okay, we're recording. So let's review what we talked about the last time in section 1.3. So we talked about evaluating limits analytically, right? Our go-to is direct substitution. If you get a value from direct substitution, you're like, great, we have the limit. If you run into the indeterminate form of 0 over 0, you're like, I have some work to do. And we talked about the different strategies that we could use, algebraic strategies that we could use. We also talked about not necessarily like one of those algebraic strategies, but becoming familiar with like Jumpman function and how you could evaluate the limit of a Jumpman-like function. We talked about evaluating a limit analytically using the squeeze theorem, right? And those three, you can think of them almost as 3 steps, but it's really like you're stating 2 conditions in order for the squeeze theorem to apply and be able to justify that the limit is equal to what it's equal to. Why is there, I don't see that on mine. Where's the,
Oh, it's probably like,
It's just like zoom in and zoom out. It should like
might just not like you.
there we go. Okay. So now we are going to be using these special trig limits, which actually can be evaluated analytically. You just don't have the tools to do that yet. It requires calculus in order to be able to actually evaluate those limits analytically. So for now, you kind of just have to trust me, and we can peek at what their graphs look like, so it makes sense why the limit as x approaches 0 of sine of x over x is 1, and the limit as x approaches 0 of 1 minus cosine over x is equal to 0, okay? So kind of think of this from the perspective of that we did with like Jumpman, how then this is just going to open up some other functions that we can think about taking the limit of. And we think of these, we kind of refer to these until you get to something called L'Hopital's rule. We refer to these as like the special trig limits because for a while you just have to like know them and be familiar with them. And like if you uncover them in a limit, you're like, okay, I can use that. So let's focus on the sine of x over x function first. Let me see if I already have that typed into Desmos. I do. Here, let me get rid of that one and that one for now. So sine of x over x, right? If you use direct substitution, so that special limit is the limit as x is approaching 0. If we use direct substitution, do you guys see that we run into 0 over 0, like indeterminate form? But graphically, we are able to see that sine of x over x is approaching 1 as x approaches 0, okay? Are we comfortable with that? Now, as for sine of x over x's reciprocal, remember when we studied like the graphs of sine and cosine, and then we studied the graphs of their reciprocal functions, okay? So this is kind of like there is a hole, like a removable discontinuity at 0 for sine of x over x. But this is sort of similar to a sine, like a normal sine curve, right? Or a cosine curve, right? A sinusoidal curve. Remember when we took the reciprocal, what happened to the graphs of the reciprocal? How we were able to use sine and cosine as guide functions, and then we knew that the curves kind of went off of those high and low points. Are we awake, you guys? You remember this?
yeah.
Totes. Okay, so if we look at the reciprocal, x over sine of x, we can see that as x approaches 0 for the reciprocal, it also ends up being 1. Right? Which makes sense to us, like that goes along with whenever we studied the sinusoidal functions and then their reciprocal, the graphs of their reciprocals. Are we following this okay?
Yeah.
Okay. So we can say that the limit as x approaches 0 of x over sine of x would also be equal to 1. Okay? And this is just the reciprocal. You can think about the graph for determining this. Now, if we thought about, think kind of back to Jumpman, how we were thinking about Jumpman. If we thought about sine of x over x as being a parent function, what would that 5 be doing to the graph of sine of x over x from a transformation perspective?
Horizontal compression.
By a factor of 5. Horizontal compression by a factor of 5. Is that going to do anything to the limit as x approaches 0? No, based on what we know about sine, nope. This limit will still end up being equal to 1. Ian, let's try this again. What's that 2 doing to x over 2 over sine of x over 2? Stretch by a factor of 2 to the that reciprocal function. So horizontal stretch by a factor of 2. Will that do anything to the limit? If you don't believe me, put it into Desmos. Okay, so looking at what we have here, and it's maybe worthwhile so that you're not thinking we're using like some completely different like thought process. If you're presented with a limit and all you're being told to do is evaluate the limit analytically, your go-to should be doing a mental direct substitution. For all of these, you guys, you see that we'd run into 0 over 0. I just want to point that out. Okay. So looking at the results of these limits, and then this like given limit that you have to memorize, can we come up with like a more general rule that we can reference using this special trig limit? Like looking at like what each of these limits ended up being?
Sine of nx over nx.
Yeah, would equal to 1. And then same thing with the reciprocal, right? So we could use the limit as x approaches 0 of sine of, sure, we can use n times x over n times x will be equal to 1. So if there's a horizontal stretch or compression, like it's not going to change what the limit is. And then this also follows for the reciprocal. Okay. How about this one? You'd run into 0 over 0 if you try direct substitution. What's that minus 4 doing to x over sine of x? To the right, yep. So shift to the right 4. Now, if this were still x approaching 0, you could use direct substitution and you would get a number. But since what x is approaching has also been shifted to the right, like you can think of that entire limit, the special trig limit, being shifted to the right. Which means that this limit will also equal to 1. Do we follow that? Okay. Okay, a little different. We're like, oh, hey, yeah, we know what that is. That's 1. Wait. No, it's not. Like, you would run into 0 over 0. But what's this missing to reference that rule that we came up with?
It's not 4x in the denominator, it's just x.
Yeah, there's not a 4 in the denominator. But how? How could we maybe get 4 in the denominator?
Multiply by 4 over 4.
I don't
Then
see
we'll-
both
Cross
sides.
side, sorry, top and bottom.
So
Numerator,
multiply by
4.
4 over 4 or 1. We're allowed to do that, right? If we think about multiplying by 4 over 4. And then this step is not required. I've told you guys you don't have to like write out applying the limit properties, but I'm going to do it for now just so that everyone can see it. Like we could then think of this as the limit as x approaches 0 of 4 times the limit as x approaches 0 of sine of 4x over 4x. And you're like, okay, well, the limit of 4 would just be 4. And then the limit of sine of 4x over 4x, based on, like, this rule that we came up with, would be 1. So this limit is just equal to 4. Okay. What about this one? You're like, oh, hey, special trig limit. Or you're like, 0 over 0, darn it, direct substitution. So what could we do? What do you have? You're like, oh, this kind of looks like the special trig limit, but
6 and 7.
yeah, they don't match. We need a 7 down here. So we could think about multiplying by 7 over 7. Sorry, I don't want that to be 76. 7 times. And there are different ways. Like I had a lot of people yesterday were like, multiply by 7 over 6 over 7 over 6. Is that what you did? You'll get there. For me, I'm like, I think I'm gonna multiply by this. So then, thinking about applying limit what am I doing? Thinking about applying that limit property, I could think about taking the limit of 7 over 6 times the limit as x approaches 0 of sine of 7x over 7x. Right? By the commutative property of multiplication, you can switch the order of those factors. And then by the product limit property. So then we would get 7 over 6 times 1, which is just 7 over 6. Are we seeing an even more generalized rule that we could come up with for the special trig limit? What do we see? Sophia?
It's, the limit is always going to be like end values.
So what if we use, like those values don't have to match, right? It ends up being that ratio. So like what if we said sine of AX over BX? And then we're like, hey, that limit ends up being A over B. Which works too, right? Like if A and B are equal to each other, then that would just end up being equal to 1. So it's just a more generalized rule, and it works for the reciprocal as well. Like if you think of bx over sine of ax. Okay, so you could either get there by thinking about multiplying by versions of 1 to make the previous more general rule for that special trig limit work, or you can just like recognize this. I do. Well, I have this one. I have one in here. Oh my gosh, whereas the last time I pulled something out, there was a ginormous finding.
B A plus C. Oh, if I'm right, I go down.
Oh, but you could use this and you could plug my charger in. Here.
Let me see.
Oh, but it has to be like a minus.
Plus.
Do you plug?
Yeah, there's a plug.
Available?
I know there's one on that side.
But like, what if C is, what if it's not 0? What if it's not 0?
Okay.
Look at the graph.
So you guys, using this, you're like, oh, the limit as x approaches 0 of 3x over sine of pi x must be
3 over pi.
3 over pi. Which you obviously first thought about direct substitution, but then you're like, 3 over pi. Or maybe you didn't think direct substitution because you're like, eh. Here's my point, though, in thinking about direct substitution. This is a little different, right? X is not approaching 0, x approaching 1. So what happens when we use direct substitution? What do we get? Say that again. Not 0 in the numerator, but we do get 0 in the denominator, which, like, oh, what's that mean? If we think back to when we were graphing secant and cosecant, right, like the reciprocal of sine and cosine, couldn't this be written as like 3x times cosecant of pi times x? But anyways, if we think back to graphing like secant and cosecant, remember what happened at the points where like sine was equal to 0 on the graph of cosecant? What type of asymptote? Vertical asymptotes, right? Like there's discontinuity. There were vertical asymptotes wherever sine was equal to 0. And you also know from studying rational functions previously, right, that whenever you have the simplified version of the equation and you end up with 0 in the denominator from plugging in a value in the domain, you know the function is undefined and that corresponds to a vertical asymptote, which means what for the limit? Does not exist. For now, all we can say is DNE. Now, for whether or not we could think about if we could say positive infinity or negative infinity, that's going to be continued in section 1.5. But my point here is make sure you are doing the mental check of direct substitution and you're not just like, oh, I see, that looks familiar. Like make sure you're like either really looking closely or always thinking about doing that direct substitution. So this is DNE. We know from our prior knowledge, one sec, that there is a vertical asymptote at x equals to 1. Go ahead, Kyle. What's your question?
Answer.
Cool. So again, my point here in giving you this one is to make sure that you are like, you're not getting too much into a groove of like, hey, special trig limit. Make sure you are thinking direct substitution first. Questions? So we're going to reference the cosine special trig limit. Here, I'm going to copy and paste it down here. If we look at the graph, here, let me get rid of this. So if we look at that graph, right, like we can see, if we plug in 0, we run into 0 or 0, but we can see that the graph is actually approaching 0 as x approaches 0. Which then it should make sense that as x approaches 0, the reciprocal, the function increases and decreases without bound, like there's a vertical asymptote. Instead of there being a hole, like in the special trig limit function, the reciprocal has an asymptote. And that should make sense with like our, like thinking back to like sine and cosine and then the graphs of the reciprocals, right? So the limit as x approaches 0 of x over 1 minus cosine x, the reciprocal, is d and e. Okay, this looks close to the special trig limit, but it's a little different. How is it different? You could do that. What if we just like factor out? You totally could do that. That is a strategy that works. I would probably, my brain goes, I'm going to factor a -1 out of the numerator, but it does the same thing, right? Yeah. So I'm going to think about factoring a -1 out, or like Jack said, you could think about multiplying by -1 over -1 to make it, to match up with the special limit. But if I factor out the -1, oops. Okay, and then by that product property for limits, if I think about the limit as x approaches 0 of -1 times the limit as x approaches 0 of 1 minus cosine x over x. Again, this is a step you don't have to show. We'd get -1 times 0, which is just 0. What's the pi do in the next one? To like, if we think about 1 minus cosine over x being 1 minus cosine of x all over x as being a parent function, what's pi do? Yeah. Which, will that do anything to the limit? Nope. Limit will still be 0. The the plus 7 graphically is shifting left by 7. What x is approaching has also been shifted left 7. Again, nothing will happen to the limit. The limit will still be 0. Okay, this one's a little different. Do we see that we could think about factoring out a 4? And then if we factor out the 4, here, I'll write this out. The 4 would cancel with a 4 in the denominator, so we would have the limit as x approaches 0 of 1 minus cosine of 11x over 11x, which that 11 would just be a horizontal compression by a factor of 11, so this is still 0. Okay, so we're going to be thinking about using algebra and these special limits. If we use direct substitution, we run into 0 over 0. So ideas on what we could do from here. How can we manipulate?
Turn it into like the limit as x approaches 0, or the limit of x plus the limit of sine x over x.
Would it be the limit of x?
Or x over x.
Of x over x. So you could,
Limit x.
yeah, so you can think about going in like the reverse of getting a common denominator, splitting that into a sum of fractions. That ends up being x over x, which is 1 plus sine of x over x. And then if we use the sum property for limits, there. Then we would end up with 1 plus 1, which is 2. For the next one, woo! Use trig identities and special limits. Okay, first of all, direct substitution. Like, 0 over 0. So then we're like, I don't see any special trig limits here. But, what can we do? Micah.
Tangent x is sine x over cosine.
Yeah, we could rewrite tangent as sine over cosine.
Also, cosine is the
You can. You earned the right to use the restroom with your answer. Just kidding. Just kidding. Should I start doing that? Like, make somebody answer? Like, that's kind of cruel, though, right? Like, you have to pee and you're like, you have to answer some math question to be able to go use the restroom. That'd be.
Restroom is equivalent.
What's the one plus
I'm
one?
pretty sure you're right.
You're like, what's the one plus one?
She, for the record, she volunteered the answer before asking. So you guys notice that this would then be able to be written as x times cosine over sine, right? X times cosine over sine, which we could split up. Oh, we don't need to split up yet. Here. So that'll be x times cosine over sine. Right? If you think about, you're dividing by a fraction, so take the reciprocal of what you're dividing by and multiply. And then, using the commutative property of multiplication, we could think about rewriting this as cosine times x over sine. And we're like, hey, we know what this limit is. So then, and I'm going to write out the product limit property. You don't have to. But we're like, hey, cosine of 0 is 1. The limit as x approaches 0 of x over sine of x is 1. So this limit is 1. Do we follow that? For the next one, let's do you three talk to each other. Let's do you the next one, and if you finish that one, then you guys can talk about the one after that.
Split it up.
I will say my example title here, I didn't actually use any trig limits for B. Sorry, trig identities for B. I did use an identity for C, but I did not use an identity for B. But you could maybe find a different way if you're like set on that. But talk to each other.
Yes.
Try B and C.
I don't think we need that.
Move into it.
Okay, we times it by 505.
I like that.
Good idea.
Ooh, yeah,
20 sine 5x over 5.
I think we should also multiply by x.
over 5x cosine
And
0.
then we split it up.
Yeah, we should split it up, And then we
Get
get
as
x equal to 0 of cosine 5x over 5x times 20 over cosine
And then we would get, what is that?
Lost.
Like
Okay,
20
hold on.
times 1
Pause.
equals
Slow down, actually.
Pause, Ian.
Okay. So we times it by 5.
By 5 and x, right?
No,
Cosine
that's 5.
of 0
Yeah, 5 over 5. Times it by 5 over 5. Yeah.
We cancel this and this.
No, it doesn't have to, you have to write it out like you have to split
And C.
it.
And C and C.
Those don't
Okay,
cancel
now.
out.
Pretty sure I
They
did
turn into
something.
one.
I see
I know.
sine of, like, what if you
So I multiplied by 5.
Wait, so
switch the x
So
and
that
y,
I
like
could get
2x?
Split it up
5x
so that sine and
And the
5x
other- Then you
over
have
5x
4
are
over cosine
together.
2x
Oh, okay.
times sine of 5x over
So-
x.
Okay.
There's gonna be two fractions,
If you
one
plug in
fraction
zero,
times the
it
other.
comes in as zero.
Wait, I just think of this as 0.
I'm forgetting all the rules.
Sine of 0.
That's very
Zero.
Yeah, but
No, I feel like I
Zero.
put it into it wrong.
It
It
goes
was
to x
too
over
easy.
zero. Because you just want
It's,
five,
it is
sine
easy. It just
five.
looks scary, but it is easy.
Math, it blows your mind, like it does mine, so.
What'd you get for B?
And then this, yeah.
Mm-hmm.
And then that
That's
equals
a lot. This one,
0.
Hmm.
The x by 0 after 1
Yeah.
goes.
oh, okay, I guess I just did it.
Can I see?
That would be what?
I've been making things up.
Okay, we're gonna group here.
Well, I don't remember I created any of these.
This would be 1,
It
right?
used to be, this is like pi,
You're close.
I said.
You
left That out would where this be 5
go.
one.
After
One?
Yes.
by
Goes
over 5.
to
There.
0
Wait.
times
This
0.
would be
Because it's cos 0.
It makes so much more sense.
Thank you.
Circle.
Oh, yeah.
Okay.
So it's 1.
And then try
20.
C. Talk to each other. Try C.
Good.
Awesome.
After you
Yeah,
B.
What are we doing for C?
Awesome. Then say
I'm a little
we
lost.
split it up.
Like you're with
Like
Gabby
a
and
banana split.
Bro,
Like in theory, I can really.
what do you mean?
I think we should do sine over 3x and cosine of 3x.
You don't need the 1 minus cosine. You should try to get the sine.
You know what I mean?
Yeah, I got
I don't know.
Split it up into sine
Sine
and
yes.
cos.
So the cosine x.
No, I understand that.
Yeah.
But why is it sine over
Oh, it's still
cos?
over zero.
Oh, yeah.
That's can.
Divide, because then it's
And then that would be sine 3x.
You guys, want to hear something funny? This
Yeah.
morning when I got dressed, I was like, I feel like I'm doing
Times,
like
no,
this
times sine 4x.
today.
No.
And then the other
Yes.
one.
Then
over
she's like
Yeah.
very
Yes.
nice. Hers is a little more elevated.
And
She's
Are
like
you-
a little more
are you-
stylish, you know?
Okay,
But
what
we're
is
wearing,
tangent? Tangent sine over cosine.
like black,
So let's say
black,
sine
and
over
like
cosine. Sine over, okay.
ish.
yeah.
What would happen if you do sine over
I feel like you're
cosine
right,
and you
it doesn't
multiply
like-
that by
like
1 over
When I
sine?
got Anne's
Does
the
the
jacket,
sine
she has
suddenly
like a
join this
similar
side?
jacket.
Yeah, it's here,
She's
Ian.
not wearing a jacket, but
Divide is multiply by the reciprocal. Multiply this
but like
by
hers
this.
is just
Yeah.
Yeah.
Bro was lost in the sauce. You're good. But now we're here.
now that we're here, we can cancel out.
What's
Sign
All
of
right, you guys, let's check in. Let's check in on B.
Sign of zero.
What time are we in here until you guys?
It's zero.
Like 59.
I want to say this is Danny.
56.
I'm gonna be so honest, I'm down.
No, I think it's Danny, guys.
So let's check in on B. Pause what you're doing. Let's check in on B. It is not C is not Danny. So what I would do for B, first of all, what did you guys get for B? The limit in B. 20. I got 20 because I just thought about, I was like, hey, sine of 5x over x. I know that. So like thinking of taking the limit of 4 over cosine 2x times the limit as x approaches 0 of sine of 5x over x. And your steps that you've written down might look slightly different. That's okay. Cosine of 0 is 1, right? So that ends up being 4 times 5 is 20. If you had more steps because you thought about multiplying by a version of 1, like 5 over 5, that's cool too. That works. You probably could have, I'm sure you could have gotten there using other identities somehow too. Like it wouldn't have changed the value, but I think you did probably need to recognize, like you probably could have manipulated using identities, but at some point you would have had to use that special trig limit. Because the x would never have canceled. Okay, next one. Did we get started with this one? This one's a little trickier.
This person, can you cancel 3 over cosine?
I don't see a 3 over cosine.
When it shows up.
Does it? So I would have seen the limit as x approaches 0 of sine of 3x, like rewritten tan, right? And I actually would have thought about from there pulling out the 1 over sine of 4x. And then I'm like, okay, cosine of 3x is not an issue. But the sine of 3x and sine of 4x, I mean, you maybe could have used some identities like double angle or angle sum and difference. I didn't do it that way. I'm just like, you maybe could have. The way that I did it is I was like, what if I multiply by a version of 1? Because I'm like thinking special trig limits. I have this sine of 3x. I have this sine of 4x. What if I multiplied by x over x? So then I could think about having the limit as x approaches 0 of 1 over cosine 3x times sine of 3x over x times x over sine of 4x. In algebra, I'm covering commutative property of multiplication today. So by the commutative property of multiplication, we are allowed to do that. And the multiplicative identity is right, like multiplying by 1, doesn't change the value of a real number. So then from here, direct substitution for that first fraction works, and we would get 1. Then times 3 times 1/4, where the limit ends up being 3/4. And if you're thinking to yourself, I never would have come up with that on my own, that's totally fine. That's why we're doing this, right? Exposure. You're kind of like seeing these different strategies that could be used for things that you haven't seen before, and building off of your experience where like if something like this came up, you recognize Like, hey, maybe I could try this strategy. Catherine.
If there's ever a sign, do you want us to do like the rule where like you get it separately and like you can, like, or could we just like at the top step, could you just plug in like without even multiplying x over x, could you just plug in 0 there, or would that lead to 0 to 0?
That would be 0 for 0 because sine of 0 is 0. So here without the x over x, you're still like, still have indeterminate form.
Okay, so we have to
substitution.
do this.
You have to do the x over x in order to get the special limits.
Okay.
That's what I meant is like, you could technically try other trig identities, like do like sine of x plus 2x and sine, cosine, cosine, sine, right? And like try and go from there, but then it's probably getting, just based on what those identities look like, you're kind of making it really complicated. It could potentially work out fine, but it would be a lot more steps probably. But like recognizing and thinking about like the different strategies that we've talked about and seeing it like, okay, I can't use algebra here, like RACCON, FOTO, anything. There is like signs in it. So maybe I could use that special trig limit and just like practice and becoming more familiar with that. Eventually, you guys, you won't even have to use this whenever you run into 0 over 0, you'll have a really like powerful tool in your toolbox called L'Hôpital's rule. But for now, this is what we're using. Okay. Any other questions before we chat about the take-home quiz? Are we ready?
Yes.
Okay. So the take-home quiz is linked here. It's also linked in the actual assignment. Due Tuesday by 3 o'clock. I made it the same due time and date for everyone because I almost made yesterday's classes due Friday, and then I was like, it's not really fair for you guys to get a long weekend.
We should all get it.
So while completing this quiz, the only resources you may use are the following: your brain, your notes, the textbook, and other people currently taking this Dorset's AP Calculus AB class. You can't use Annabelle. You can't use Michael Bradley. You can't use Leo. Okay? You can't tap into, you can't use if you have a tutor, you can't use a tutor, you can't use Joey. Okay? Nobody else besides people who are taking, you can use people from other sections. Julian.
Can we use Dorset if we're here during office hours?
No. So, but great question. I'm glad you asked. I will still answer questions about the 1.3 practice or problems from the notes or textbook. So problems that are not on the quiz, I will still answer questions about, but I will not, and you can't go ask the teachers that are in math. They have to be in my class, so any of my sections in my class. So again, I will answer questions about problems that are not on the quiz, like you have the 1.3 practice to finish that's due on Friday. No, Friday. When would it be due for you guys? The 1.3 practice would be due Monday. Tuesday. Oh, so you have both days. Sorry. The other class has theirs due tomorrow, the 1.3 practice. Now, no internet, no apps, no AI, but like, I know you guys are smart enough not even to trust like AI, right? It can be confidently wrong. You need to make sure you are showing work. Now, just because I'm saying you guys can work together, it doesn't mean you can like all copy off of one person, right? Like you guys know that, and that's not going to benefit you for like, we are going to have a test on chapter 1 coming up, and I can tell if you have copied, and I can tell if you've like Wolfram Alpha, because oftentimes like Wolfram Alpha is a more complicated way of doing things than how I would teach it. Are there any questions on that? I also also wouldn't save it for like 2 o'clock on Tuesday. Because it's like 8 pages long. It's probably longer than what it would have been if we'd taken a quiz in class.
Is there a time limit on it or anything, or can you just like?
This is kind of best.
Till Tuesday at 3 o'clock.
So
So
I
it's
could
like
spend.
several hours.
Like my
Could I spend like take like a 4-hour phone call with someone else in this class? You.
Yeah.
Okay.
Well, that
Don't have a quiz?
Okay.
I feel like.
Any other questions before we move on?
They didn't grow up in the school system.
Yeah, your parents can't help you. You can't ask parents. No help from parents. No help from brother. No help from no one
Pets.
besides people in your class.
Pets?
Who?
Stuffed animals.
Yeah, sure.
Can I give my
You can
cat
teach them.
Imaginary
You can
friends.
teach them about
Can I
it.
keep my Apple ones to my cat until it like randomly?
If my imaginary friend has already taken.
I don't know if this is the right class to do something like that. All right, you guys, let's switch over to section 1.4. Once we get to where I stopped with the other classes, I'll let you have time to start working on the 1.3. I would complete the 1.3 practice before starting the quiz, would be my suggestion. And you shouldn't be working on the quiz right now,
Yeah, Ian. Imagine working on the quiz.
Kyle.
Couldn't be me.
No working on the quiz right now.
I was just like putting it was just
It was just Ian.
I already.
You like gave yourself away right away, too.
That's real one.
I didn't even suspect you. I was just saying. I actually suspected Jack.
Oh no, I already.
Jack already finished.
Yeah. Because Tony asked me to work with him, and I was like, that's cool.
You already did the quiz.
Yeah. Because I had a free period, I thought it was fun. I didn't actually know.
You hadn't finished the lesson.
No, I didn't even take I hadn't even looked at the lesson you posted for me. Yeah.
All right. So you guys remember the reason that we have hard copies of the textbooks is that the digital copies were really funky. The previous version, just left off characters all over the place. This is a screenshot of an image from there. So first item of business. X approaches C. This should be X approaches C, and this should be not equal to. So add that in.
Maybe it's like a design choice.
To just leave off characters.
Yeah.
Like in the limit in chapter 1, literally all the arrows not there on any of the
Might
limits.
have been like it doesn't work with the.
Yeah.
It was a
exactly.
PDF. Yeah. It was a Kindle.
Maybe like when they put it in, like the characters.
It was mini Kindle.
But then they're update the 12th, that was the 11th edition.
Yeah.
You might have noticed you used the 11th edition for the summer thing. But the 12th edition then was just missing multiple pages from every single section. Also, PDF, Kindle. Where did they go? How did that happen? Big whoops. And how did no one notice before, pushing that out to...
I don't know why this for the summer program, I actually wrote down a bunch of problems wrong or they were misnumbered in the textbook because they didn't match the ones in the answer key, and I was really confused as to why I never learned how to do them. So I just wrote
Well, were
down
you
different
looking at
wrong
the 11th edition in Calc Chat
No.
or the 12th edition?
I didn't think of the one that you sent me.
I'll look at it again. I'll double check it.
Also, I could have just done it wrong.
I'll look at it. I mean, it's possible that I put the wrong.
No, but
All right.
I have 5 problems, so I could have done it wrong. That's entirely possible that I was brain dead.
For fun.
Yeah.
So you guys, section 1.4 is going to feel very familiar because we're basically taking everything, we've talked a lot about continuity in the past, right? Continuity, different types of discontinuities that occur. But we kind of have this informal definition of what it meant for a function to be continuous, at a point or on an interval, right? In pre-calc, we were if you can trace your pencil along the ground without having to lift it, then the function's continuous. Like that's like a weird definition, right? Or like anytime you have to lift your pencil, then it's a discontinuity. And for like our classification, like what a removable discontinuity is, I was like, if you could think about imagining removing the discontinuity by filling in a point, then it's removable. Otherwise, it's non-removable, right? So we're going to have like, now that we have limits, we're going to have a more formal definition of what it means for a function to be continuous at a point and continuous on an interval, okay? Kind of the worded version, the not like tracing the graph, but same idea, informal definition of continuity at a point is if a function f is continuous at x equals to c, then there is no interruption in the graph of f at x equals to c. You don't have to lift your pencil to keep tracing it. That is, the graph is unbroken at c. There's no holes, jumps, or gaps. Same idea as like the tracing, right? The following are examples of different cases where the function is continuous everywhere on an open interval except at x equals to c. Right, like so this first graph, f would be continuous on the open interval from a to c, and then from c to b. This next graph, the graph would be continuous on the interval from a to c. C could actually be included, and we'll get into that based on now our knowledge of limits. Like previously, whenever I talked about continuity to you guys in pre-calc, I explicitly told you, like, identify the open intervals where a function is continuous. But now that we've like talked about limits and one-sided limits, we'll be able to think about like what's happening at an endpoint. Is a function continuous at an endpoint of an interval? And then same thing. So last one from a to c, open interval, and then c to b, the function is also continuous. All right. Here is our formal definition of continuity. This is really important. It seems kind of like continuity doesn't seem like at the moment, right? Like it's like that major of a thing. But like it's super important for like understanding when a function is continuous or if there are discontinuities for a function, okay, or at a specific point. Being able to interpret given information and understanding like what it's saying about the continuity is really important. So our definition for continuity at a point, you can almost think of as like a checklist, okay? And it has 3 points, a checklist with three bullets. So a function f is continuous at c when these 3 conditions are met. And if these 3 conditions are met, like check, 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 then the function f is continuous at c. If one of the checks isn't checked, okay, like if one of them fails, if one of those conditions fails, then the function would be discontinuous. But it's in using this definition to determine if the function is continuous at a point that you can determine like what type of discontinuity would occur. And that's what this is all about, right? Like we're trying to identify different characteristics. Before we did it from like an algebra perspective, but now we're starting to look at functions from a calculus perspective. And we're focusing on continuity, okay? So if f of c is defined, meaning you plug in c into the function and you get an output. If you don't get an output, you're immediately like, oh, well, f is not continuous, but you're not done. Like if you're trying to figure out like what type of discontinuity occurs, then you would go to the second item on the list, right? So think about the limit as x approaches c. If it exists, that's going to tell us something about the continuity, which we've kind of been discussing this whole time, or about the discontinuity. And then for the function to be continuous, if the function is defined and the limit exists, and those values are equal to each other, then the function is continuous at c. So like that first case of when the limit exists that we had talked about, right? That's whenever a function would be continuous at c. And then for continuity on an interval, a function is continuous on an open interval when the function is continuous at each point in the interval. If you have an open interval, there are infinitely many points on it. You're not going through this checklist for all the infinitely many points. In order to determine that a function is continuous on an interval, you're having to rely on your prior knowledge, like your pre-calc brain, to help you. If you're kind of trying to determine if there are any discontinuities, again, you're kind of having to rely on your prior knowledge of functions that you studied in algebra and pre-calc. A function that is continuous on the entire real number line, negative infinity to positive infinity, so you could trace the entire graph from negative infinity to positive infinity, you could say that that function is continuous everywhere. And I point that out, or everywhere continuous. I point that out because there are often times, like in a free response question, where you'll be given information about the continuity of the function. And I'm telling you now, and you'll hear, I'll probably sound like a broken record by the end of the year, all of the information that they give you in a free response question matters. So like the fact that they're giving you, like a function is continuous everywhere, it matters for the problem. Okay? Whether you actually have to use it in your justification or not, like sometimes you do, sometimes you don't. But like them making that statement is so that there's no holes, there's no like gaps in like the problem or like alternative interpretations. Are we doing okay, you guys? This should look kind of familiar. I give you guys a similar kind of like, what would you call that? Like a flow chart? In pre-calc last year, I didn't say anything about limits. I kind of interpreted the limits, in other words. But remember, there's two types of discontinuities. There's removable and non-removable. Graphically, for removable discontinuities, we've talked about like if there's a hole or if it's like a piecewise where like it looks like there's a hole but the function value is actually something else. And now that we've talked about limits, we can say that if there's a removable discontinuity, the limit has to exist, right? Like the function has to be approaching a number. It's just that maybe the function is undefined if there's a hole, or the function value is something different. So case 2 or 3 of when the limit exists. If the limit does not exist, that tells us that there is a non-removable discontinuity. You will never be asked to classify the type of non-removable discontinuity, but for us in discussion, it's easy enough to understand, right? So if the limit is DNE, you're like, oh, it's a non-removable discontinuity. If it's DNE because the one-sided limits both exist, but they're not equal to each other, then it's a non-removable jump discontinuity. And we've kind of talked about that. If the limit doesn't exist because the function is either increasing or decreasing without bound, like going to positive infinity or negative infinity, as x approaches c from the left or the right, then that's whenever we'd say there's a non-removable infinite discontinuity because we're kind of like in the reverse of like understanding that. Like it's because of that that we can conclude there's a vertical asymptote, but you guys have learned about vertical asymptotes already. But again, it's when that's true that we're like, there's asymptotic behavior. There's a vertical asymptote at whatever x equals to cs. Are we okay with that? Okay. Now, before we get into this example, notice that it says discuss. we are about to have a discussion about the continuity of this function. We are not right now thinking about how will something like this appear on the assessment. Okay? I want your focus to be on understanding and following along and participating and what it is that we're talking about with this function, because this is a function that you're familiar with, right? This is a rational function, which you've studied before. So, kind of putting on your pre-calc brain for now. Officially writing it down. So officially putting on the pre-calc brain. If we're just looking at that equation, don't even think about doing any algebra yet. Just looking at that equation, what could you tell me about the function? Micah?
There's like an asymptote at x equals 2.
Well, do you know if it's an asymptote?
No, like a discontinuity.
There's a discontinuity, right? Because, how did you come up with 2?
Because x minus 2 is in the denominator, so 2 can't, like x can't be equal to 2 or else it's something over 0.
Exactly. 2 would make the denominator, by inspection, 2 would make the denominator equal to 0. So like if you were being asked, like think back to pre-calc, if you're being asked about the domain of this function, you would look at it and go, okay, well, x is all real numbers except for 2, like negative infinity to 2 union 2 to infinity. So with our pre-calc brain, we're like x can't be equal to 2. Also relying on your prior knowledge, right? You know that's the only domain restriction. So everywhere else is going to be continuous. Like just because you know that, you are familiar with rational functions, right? Like the only potential point of discontinuity, or the only point of discontinuity, is 2. Right? There's no other domain restrictions. And you guys understanding, like, that's a rational function. There's not going to be a jump, right? That would have to be like a piecewise or something. Like 2 is the only potential point of discontinuity. Okay? So then, let's think about using our definition of continuity at a point. And examine deeper what's going on with this function at x equals to 2. So first, if we think about evaluating f at 2, what happens? We know we get 0 in the denominator. What do we get in the numerator? 0. So actually, from a pre-calc perspective, like you guys already know what the graphical manifestation is, right? What happens from having your pre-calc brain on, like what happens at 2? If we end up with 0 over 0 when we use direct substitution here. A whole. Okay. But again, we're kind of looking at this now. We're having this discussion from a calculus perspective. 0 over 0 at this point, we're just thinking is undefined, which is a red flag for discontinuity. Like we immediately know, hey, f is discontinuous just from thinking about substituting in 2. We got started with 2 from using our prior knowledge. But like if you were being asked a question about like, discuss what's happening at x equals to 2 for this function f, right? Like you just think about plugging 2 in. So then we move on to the next part of our definition of continuity at a point, which is taking the limit. So thinking about taking the limit as x approaches 2 of f of x. We're going to think about following that puppy. And notice that I referenced the function as f of x. That's fine because it's been defined as f of x. I wouldn't just put the limit of the factored version of the rational function, but because I referenced the original function by stating f of x, that's fine. Okay, x minus 2's cancel. From your prior knowledge, you know that the graph of f will look like x plus 3, but has the domain restriction that x can't be equal to 2, right? You know from what us studying rational functions last year, there's a hole there. But now we're having like a more rigorous definition other than being like, oh yeah, factors canceled. So that means there's a hole. So we end up with, I changed the number. Did anyone notice that? Just making sure you're paying attention.
Oh,
Oh, I thought it was just a really.
yeah. I was gonna, I was
Two, like, I thought
it
it
was
was
a 2.
Oh.
Two that had been through. like,
Should that be the like trick? Just have really messy handwriting and then you won't know. You won't be sure. What does that mean?
I thought it was f of a.
Same.
0 to 0.
Yeah.
I was-
Okay.
I felt that one.
Because the limit exists. Not limite. The limit exists. We can conclude that f has a removable discontinuity at x equals to 2. Wow, with the bell, you guys. That was good. Okay, we will pick back up with 1.4 on Tuesday. So I won't see you guys until after the long weekend.